Hi everybody, I'm Eric from Team 6637, the Beta Wolves from Kearney, Michigan. This video is the last video in a multi-part series about coding a drivable robot using Java with command-based robot project. This video, I'm going to just recap what we've done in all the previous videos, but I'm going to do it much quicker. I'm just going to code out the whole robot from scratch, getting a basic robot driving. So we're just going to jump in, but if you haven't seen the previous videos and any of this is confusing, I would watch parts 1, 2, 3, and 4 and then come back to this one as a recap. But let's get right into it. To start a new project, I'm going to show all commands in VS Code, which is Shift-Command-P. And create a new project is right up here at top, but if it wasn't, I could start typing create and it would show up. And I'm going to use this and just go through. I'm going to make a template in Java and select command robot. The folder I'd like to place it into, I'm going to select project folder, and it's going to be in this VS workspace. So I would click on VS Code workspace and select that folder. Project name, let's call it Drivable Robot. I want to make sure that's not already in there. No, I called it my Drivable Robot before. So Drivable Robot works. Well, how about I say Drivable Robot Recap? It really doesn't matter. Team number 6637. And I'm going to generate the project. Yes, I want to open it. And here we are. I'm going to open up the source and go right to the OI. The OI is the operator input, such as a joystick. So the operator input that we need for driving a robot would be our joystick. I'm going to make this public so it's available outside of this class. And I'm going to set the port to 0. We'll be coming back to that in a minute when we work with our robot map file. Instead of putting our port directly right here, we're going to make a variable that represents it. And then we're going to stick that variable there. So I'm going to organize my imports. So right click. Oops, that didn't work. Right click. And usually it lets me organize imports. What if I right click right on this? Save it. It is not working like it did before. Let me hover over this like I would with Eclipse. It cannot be resolved to a type. So I'm not really sure why it's doing that right now. It didn't do that before. There's a little light bulb here. I clicked on that and it says import joystick. Okay, let's do that. So now it imports it up here. The class is wpilibj.joystick. That's where our library pulls in from, and the code is happy. So let's go with that. The other file next that I'm going to go into is the robot map. Now the robot map is where we map physical ports on the RoboRio to hardware that we want to use. So when we're creating a robot, we want to keep track of our ports here. And I'm talking physical ports on the RoboRio that you would plug something into. We need to know what port that is so the RoboRio knows which motor controller is plugged into which port. And then it can control it properly. Another thing you might put in here are constants, and constants are variables that just are always staying the same, such as the wheel diameter on your wheels on your robot. You might need that for math later on, and that number is not going to change, so we put it in the robot map. And if any of these ports change at any point, like someone moves the wire to a different port, then you know you can come to the robot map file because it's all in one place. So let's just get started right away. I'm going to say public static int. And I got a little clue of why I typed that, because it's right here for these other examples. Public means it's used outside of this class. Static means that this class doesn't need to be instantiated for this variable to be useful. Don't worry about that if you don't understand what that means. And int means it's going to be an integer. So we have left master. So public static int left master equals 1. So the left master here, if I have two motors on the left side of my robot, one's going to be a master and one's a slave. Okay, and that's because I have talons. And with talons, I can say, this is the master, I'm going to control you, and this is the slave, you follow whatever this one's doing, and we'll be setting up that code later. But if you don't have talons, you might want to call this something like left motor 1 or left motor front. Whatever your naming convention is for your team, go for it. But I'm going to be naming this left master, and the port that is physically plugged into is port 1. We also have a left slave equals 2. Right master is plugged into port 3. And our right slave is plugged into port 4. A moment ago we were in the OI file and we plugged in port 0 for the joystick. So I'm going to make a variable for that, and I'm going to call it joystick port equals 0. And also, I forgot, I'd like to put the word port up here just to keep this super didactic. When we use this later on, we'll know exactly what this variable represents, and it's actually a port. Apologize, I forgot to do that. Left master port, left slave port, right master port, oops, this needs to be a capital M, and right slave port. And then here we have joystick port. The naming convention on our team is to use camel caps with variables. The first letter is lowercase, and then every word after that, there's no space, you just capitalize the word. Camel caps because it's like humps on a camel, right? So how do we get this joystick port into the OI? We use something called dot syntax. So instead of having a 0 here, I'm going to just type robot map because that's the class name that we're using. We didn't instantiate this to an object, but it's okay because these are static variables. So I can dig into this robot map right away and grab, see I can go up and down with my key and go right to the joystick port, and boom, there it is. Robot map dot, it digs into the robot map file and finds the joystick port. This right here, this variable would output a value of 0 because that's what we set it to right here. Okay? So that's all we need to do with that file, and the OI file as well is all saved and ready to go. Real quick, the robot file is the hub of the robot. So that's all three of these, OI, robot map, and the robot. Those are the 3 default files that you're going to need to use. The robot file, every robot, see this is our class, robot, you have to instantiate a new version of the subsystems. And we're going to go over subsystems in a minute, but basically you'd be creating a class for your subsystem and then a variable that you instantiate the class to. And then from then on, you could say with dot syntax, robot dot subsystem, and then you could hit dot and do anything to the subsystem that you've set up. In this case, we have this example subsystem. I'm going to comment this out because we're not using that subsystem for our drive. And notice here, it's giving me this squiggly line. I'm going to get rid of this because it's unused, this import here. We don't need that. And another thing that's bothering me here is I don't like these M underscores anywhere in here because I just don't like that naming convention. Notice that they've created this class, or they're casting this variable. They created this variable name and they're casting it as OI. But I don't like the M underscore. So I'm going to hit Command F to bring up my find screen. Hit this to get find and replace. And we're going to find the M underscore and replace it with nothing. And here's replace all. Boom. That takes out all the M underscores and just kind of cleans this up. OI equals new OI. Again, if this is like stuff you're not understanding, like what's a class, what's a variable, how are we instantiating these variables to make these an object, then you certainly should watch the first 4 videos in this series. But I'm going to continue to fly through this. I'm going to save that, and that's all we're going to do right now in the robot file, and I'm going to close all 3 of these. The next thing we're going to do is create a subsystem. I'm going to right-click on this and hit Create New Class command, and I'm going to select Subsystem, and then I'm going to type Drive Subsystem. Enter. Now the Drive Subsystem is just a class that represents the hardware that's required to drive our robot. Now, with this simple tutorial, we're just going to be talking about motors in here. But if you have a gyro and you have encoders, you might want to consider putting them into the drive subsystem class as well, so that everything can be controlled in one place that relates to the drive subsystem. Excuse me. So the first thing I'm going to do here is just define some of my motors. Public WPI lib talon SRX left master, I'll describe this in a second, equals new WPI talon SRX, and they want a device number, which is the port. I'm going to give it robot map dot left master port. Okay, so what I'm doing here is I'm setting up a variable that represents my left master motor. Okay, my motor is plugged into a Talon SRX motor controller. The Talon SRX motor controller is plugged into the RoboRio port 1, and that's what robot map dot left master port represents. If we go back to the OI, whoops, I'm sorry, the robot map left master port equals 1. Now, it's not physically plugged into the RoboRio per se, because in this case we're using the CAN drive. Now the CAN drive is a series of daisy-chained wires. So it comes out of the RoboRio and it goes into Talon 1, and that goes into Talon 2, and then it goes into Talon 3. But they each have an ID. And this one's ID is 1. But if you had Sparks would be physically plugged into the RoboRio via a PWM cable. All right. If you have the old Victor SPs or the Victor 888s, I believe those are PWM cables as well that plug into the RoboRio, and that's what port it would be plugged into. We're going to talk about Sparks and other non-Talons in a minute, but basically we're saying, okay, this is a Talon SRX. We're going to name it left master, and we're going to refer to this motor as left master moving forward. And that's a new instantiation of that WPI Talon SRX class. Okay? And it needs to know which port we have, so we plug that in there. Okay, so public left slave, and the slave would be plugged into left slave port. All right, we're going to do this 2 more times with our right master. And our right master port. And I'm going to see if I can save some time by copying and pasting here. We have our, sometimes this is not as much of a time saver as you'd think. Right slave, and it would go into the right slave port. Well, I guess that did help. Okay, so now we've defined our motor controllers. Okay, and I don't really remember to do what's next, but I don't have to, because I can jump over to the resources page on betawolves.org, and I can go to the Google Doc lesson, and I made it all the way into the drive subsystem before I remembered what to do. And oh yeah, here's the comments that I can follow. Let me go back. We already instantiated these motor controllers. The next thing we need to do is instantiate a differential drive object. Now, differential drive, as you might recall, is a class that WPI lib made that we basically put our motor controllers in, and then we don't have to touch our motor controllers anymore for this kind of stuff. We just tell it with this differential drive what to do, and it's very simple. From then on, we just basically say how fast do we go and how much do we want to turn, stuff like that. So I'm going to say public differential drive, and then I'm going to name it drive equals new differential drive, and it wants a left motor and a right motor. Now, since I'm using Talons, I'm just going to pass it the left master and the right master. And then, oh, this is what I'm doing right now. I'm going to move this up here. Then I can create a constructor function. Follow me, follow me. Just bear with me here. I'm going to call it public drive subsystem. Notice that it's a constructor function is named the same thing as the class. We got our parentheses and our curly braces. And inside of there, I'm going to point my slaves at my masters. Oopsie. So I'm going to say left slave dot follow left master. And then I can say right slave dot follow right master. So since I have talons, all I have to pass the differential drive is the left master and the right master. And anytime we call this drive instantiation or this drive object and we tell it to do something, it's going to control our left master and our right master. And our left slave and our right slave are just going to follow the left master and right master, so we don't need to worry about them anymore. So this is all well and good if you have talons. But if you have something else like a spark, this will not work. So let me show you real quick what I would do if I had a spark. And I'm gonna copy. I'm gonna highlight all this and hit Command and then the right slash, which is right under the question mark, and it just comments all that stuff out for me. And I'm gonna instantiate a spark. So I would say public spark, and I'm gonna call it left motor or left front motor. Whatever your naming convention is, that's fine. Equals new spark, and I'll just tell it port 1 just to save a little time. Public spark left rear motor equals new spark 2. Let's copy this, paste it, and then we'll have the right front motor and the right rear motor. And those would be ports 3 and 4. So now if you have sparks and they're plugged in with PWM cables to ports 1, 2, 3, and 4, and I highly recommend putting those ports into variables like we did with the robot map. You get the point. You then have to pass these motors into this differential drive, but please note it only takes 2 variables. So you could pass it your left front and your right front, but from then on you would only be controlling 2 motors and the other 2 wouldn't be doing anything. So in order to pass it all 4 motors, we need to create speed controller groups. So I'm going to create a speed controller group. So first I say I'm going to cast this variable as a speed controller group, so I have to say the class name there, and I'm going to call it left motor group equals new speed controller group, and it wants some speed controllers in here. So I'm going to pass a left front motor and left rear motor. Now, left motor group represents both of those, and I can pass it the left motor group into differential drive. Let's try that again. Speed controller group, right motor group equals new speed controller group, right front motor, left, right rear motor. And I would take right motor group and I'd put it into here. So now our differential drive is going to be controlling both of those. And at that point, you would not need this right here. Okay? And you'd be at the same place with sparks as you were with talons. I'm going to undo that since I do have sparks. I'm going to go back to where I was earlier, and we will move on from there now. Clean this up a little. Having tidy code is wonderful. So next thing we need to do, and I don't want to call this teleop drive, I want to call it manual drive. We have to add that manual drive method. Okay, so I'm going to do that right now. I'm going to say public. It's not returning a value, so we're going to say it's void manual drive. I'm going to open and close the curly brace. Now notice this class up here has an opening curly brace and it closes down here. Everything in between there is part of this class. This, since it's got a an opening closed curly brace here, is called a method. And you can call methods, which basically, to do that, I would say robot.driveSubsystem.manualDrive. So you dig through dot syntax through the hub of the robot, and you dig into the drive subsystem, and then you can call one of these methods by saying .manualDrive, and it would execute all the code that's in here. So what I want to do is I want to make my robot drive. So I would say drive, because I'm using this differential drive up here, dot arcade drive. You can use tank drive if that's what you're into, swerve. If your team does, well, it wouldn't be swerve under differential drive, I don't think. Regardless, if you wanted to use tank drive instead of arcade drive, you could say drive.tank drive. But we use arcade drive. And all you need to pass arcade drive is your speed and your rotation. In our command that we're going to build in a second, we get the speed, which is our forward and backwards on the y-axis, and we get our rotation, which is our left and right on the x-axis. So we're going to call a command that uses this subsystem and tells the subsystem what to do. And basically, every time the control loop spins on the robot, which is, I believe, every 10 milliseconds, it's going to say, oh, what was that joystick value? Hey, drive at that value. And it's just going to do that over and over and over at super fast speeds. So we're going to tell it how fast we want to move and how fast we want to turn. But we have to pass that through this method. We're going to get it in the command. We're going to grab those values. We're going to say, hey, manual drive, go this and turn this. So we're going to pass it those values as arguments. So I'm going to say double move and double turn. Now, double basically just means it has a decimal, right? If it was an int, it would be a whole number like 1, 2, 3. But this could be like 0.675, right? So we need to tell it it's a double. We can't just put a variable in here without telling Java what this variable is, because Java expects to know. You have to tell Java quite a bit about what's going on in the code. So I'm going to be creating a command that calls this manual drive and tells it what our y-axis value is, how fast we want to move, and tells us what our x value is on the joystick, which tells us where we want to turn. And it just passes it into this arcade drive method that comes with the differential drive class. We didn't have to code that, thankfully. WPI-lib did. Super simple. Save it. We're done here. Next thing I'm going to do, as promised, is I'm going to create a command. Actually, before we do that, why don't we go into the robot file and pull in this subsystem? Because the robot.java file is the hub of our system, and it needs to know what our subsystems are. And you can see right here that the example subsystem that came with it was already instantiated, and we just need to emulate what they put there. So I'm going to say public static drive subsystem, because that's the class we made up, and we're going to name it now. I'm going to call it drive subsystem with a lowercase d, because remember, our variables have a lowercase out front, but any classes you create have an uppercase out front. So it helps you visually, just looking at things, knowing whether it's a variable or a class. So it's going to equal a new instantiation of drive subsystem. Whoops. And that's it. Now our robot knows about drive system, and we can call drive subsystem by saying robot.driveSubsystem. Saving that, and I'm going to create that new command. I'm going to right-click on commands and hit create a new class command, and I'm going to pick command, and I'm going to tell it it's a manual drive command. How about that? Once that opens up, here it is, manual drive command. This is the constructor function. Certain code needs to go in the constructor function. One thing you have to do is you have to tell it which subsystem your command requires. So remember, we can dig into our robot and say .drive subsystem now, and that's telling this command what subsystem it's commanding. And that's helpful because you don't want multiple commands commanding the same subsystem because you could get unexpected results, and that could be disastrous for your robot. The initialize method just runs once when your command is fired, execute loops over and over and over again, is finished, returns a value of false if it isn't finished, and true when it is. We won't need to worry about that. Sometimes you might want is finished if you're like driving a certain amount of distance. You'd say, okay, is it finished? Have we driven that far? And as soon as you have, then it'll say yes, return true, and this command will fire the end method, which happens once at the end. So you might want to clean up something with some code, like reset your gyros or something. And then interrupted would be like if another command starts up that also requires a subsystem, such as we did here. It would interrupt this command, and this could potentially fire some code in here that you might want. All right, so the only thing we really need to do is we need to get the value of our x and our y from our joystick, right? So I'm going to say double move, because that's what we want to say for going forward and backwards. That's our move, and that's our joystick right here. Our y value, I'm going to grab that joystick. So move equals robot.oi.stick.getY. And that's it. Well, that's nearly it. That will get our up and down. But unfortunately, just to add a little bit of confusion, joysticks such as this and even that big joystick that you might have got in your rookie kit, going forward is -1. Going backwards is 1. We want our robot to be tracked between forward, which is 1, and backwards, which is -1. So if you want it to tell it to go forward, 1 means full forward. That means give your motor full power. 0 is neutral, or giving 0 power, and -1 would be full in reverse. But like I said, this would be -1 on a joystick. So all we have to do is negate this number by putting a negative here, or saying -1 times the y-axis, right? So that's basically all you need to do there. So next we could say double turn equals robot.oi.stick.getX. And then, we have some variable issues here. What's the problem? Value of the local variable move is not used. Oh, well, I'm about to use it, so don't worry about it. So I'm going to tell my robot what to do now. Robot.driveSubsystem.drive. We could just call, oh no, I don't want to call it drive. See, we could just call drive.arcade drive and tell it our move and our turn. But in our drive subsystem, we're making up a custom method, and then within that method, we're passing it our move and turn, and we're calling drive.arcade. And we do that in case we want to add some other math here, some other calculations that we want to always do on the robot. So we would do it in our drive subsystem here once, and then we call this manual drive, and it kind of like puts our spin on this robot. No pun intended. Okay, so in our command, I would pass it the move, and oh no, we're not using this. I'm sorry. We're going to say robot.driveSubsystem.manual drive. We're going to pass it move and turn. And there we are. We are done. Practically. Could that be it? Should that be it? I'm going to save this. I'm not getting any other errors. There's an issue here with our example command. We aren't using this example command. I'm just going to delete it and see if that causes or fixes more problems. We also aren't using example subsystem, so I'm going to delete that as well. Looks like we have a couple issues now with our robot.java. If we go there, let's take a look. First of all, our import is referencing this example command, which it doesn't exist, so I'm going to delete that. We have one issue left. Down here, we're also calling this example command. And just for the sake of simplicity, I'm going to change this to our command that we just created, which is manual drive command. And now we are PT keen. Another thing I want to mention real quick in our drive subsystem, Down here we have this init default command. I'm going to uncomment this and set that command as our manual drive command as well. That's basically if no other commands are controlling this subsystem, what's the default going to be? What is it always going to go back to when other commands are finished or when it starts up? And in our case, we want that to be our manual drive. So that is done. Clean this up a little, save it, and that's our robot. You might want to put a little bit more math in here. Again, this is in the drive subsystem, this manual drive, so you could deadband the joystick. And I think we went over that in our command part 4, the command portion of the videos that we created. So if you want to watch that on how you deadband that, that's basically so when this is sitting still, it might give you like a minute value because it's an old controller, and it could tell your robot to start driving forward real slowly even when your hand's not on it. So you want to make sure that any minuscule values return 0 and don't control your robot on accident. So you can do that there. You could also set a max speed. And there's probably tutorials on that, and that's so that you can set a constant in your robot map that says we only want to drive at 0.5 or we only want to drive at 0.6 because we're testing right now. And then once it's time to go to production, when it's time for the competition, that value you could change it to 1. We want to go full speed now, and basically you could govern your system here to only move at that value. So in its simplest form, you could say if move is greater than 0.5, move equals 0.5. That would reduce your speed to half even when your joystick is going full forward to 1. This could be saved as a constant in your robot map, so you could eventually say robot map.max speed. So my point here is not to code this stuff out, but to show you why we would create a manual drive method and put our drive code in there. It's so that we can do this math here if we want. Okay, that is it. I hope that was fast enough. It looks like we're just over 32 minutes here. I tried to keep it lower, but this is the end of this series. I really hope it was helpful. If there's anything else you want to learn at a real basic level, let me know and I'll make some videos on it. Thank you so much. Hope you have a wonderful FRC season.